All right, let's get started. So last time we left off starting to talk about the Schrodinger equation. Which is given by something like I times ut equals c squared uxx. Actually, sorry, I was in the wrong place, and let's see here. Something like this. Okay. And we're going to impose some boundary conditions. So we'll just fix the endpoints. Zero. Okay. And so let's derive the solution to this equation by using separation of variables. Okay. So assume that your solution is of the form f of x times g of t. Okay. So this is a big assumption, but we're going to do that anyways. And so now let's plug it into this equation. So ut is f of x and then g prime of t, where this prime is on the t variable. Okay, hopefully it's not. So I'm going to start using primes for f and for g, but they are taking the derivatives of its own variables. Okay, so hopefully it's not too confusing. And then uxx is equal to f double prime times g of t. Okay? Because you're only taking the x derivative, so you would only take the derivative for f of x, which is the function of x. Okay? And so when we plug that into the Schrodinger equation, we get f of x times g prime of t, that's ut, is equal to I times f double prime of x times g of t. Okay. And now if we divide both sides by f and g, then we get something like this. So we have, well, let's also divide by I. So this is going to be g prime divided by I times g of t is equal to f double prime divided by f. Okay, so far so good? Okay, so now this side is a function on t, and this side is a function on x, but they're independent variables, so they shouldn't depend on each other, which means the only way this is possible is if this whole thing is a constant. Okay, and this is equal to some constant. And I put negative here for convenience. Okay. And so now we're going to solve each of these ODEs separately, right? But before that, let's show why I even put a negative sign here. So from here we get f double prime of x is equal to negative lambda f of x. Okay. And if you look at this boundary condition a little bit more carefully, what this is saying in the separated case is that f of 0 times g of t is equal to f of L times g of t is equal to 0. Okay, this has to happen for all t, and you don't really want g to be 0, or else you use just 0, which I guess technically would satisfy this equation, but you want to avoid that trivial case. So then we know that f of 0 and f of L are 0. Okay, these aren't functions anymore, right? Because you're plugging in 0 for x and L. So at these specific values, f is 0. So we know that f of 0 equals f of L is 0. Okay. And so before we actually go about solving that one, right, let's analyze a little bit about what we can say about lambda, the constant. Okay? And so this should remind you a little bit of the energy methods that we did before, right? What we can do is multiply both sides. By F and integrate. From 0 to L. So when we do that, we get the integral from 0 to L of F double prime times F of x dx is equal to negative lambda integral 0 to L F squared x dx. So far so good. I just did what I just wrote here. Alright. And then just like the energy methods, right, we integrate by parts here. So integrating by parts, we can throw one derivative to this guy. And so we have negative 0 to L of F prime squared dx, right, plus the boundary terms. Right, this will be F of x, F prime of x, evaluated at the boundaries, L and 0. Okay, so this is just integration by parts. However, we can use the boundary condition that at 0 and at L, F is 0. Okay, so in fact this boundary term goes away. And so we get that negative lambda integral of F squared is equal to negative integral F prime squared. Okay. And so now you can kind of see that this side is not negative. Because you're integrating something squared, and then you have the negative here. And over here, you're also integrating something square, so this is going to be a non-negative. Did I say non-negative? I meant non-positive. Anyways, this is non-negative. And so this lambda needs to be positive, right? Because if lambda is negative, then then you would get that this whole thing is 0, which you don't really want. So this tells us that lambda has to be greater than or equal to 0. Okay? Because we just plug in some negative number into here, you'll see where it kind of goes wrong. All right. So from the boundary conditions, we can conclude that lambda has to be 0. Has to be positive. Okay. And so that's why I put a negative sign here. Because you can rewrite this equation in like a little bit kind of like better looking form, which is F double prime plus lambda F equals 0, where lambda is positive. Okay. So far so good. And it's kind of important that it's positive, right? Because these eigenvalues are supposed to represent frequencies of like a string, so you don't want like negative. Okay, and so now that we know they're positive, so this time makes sense, we can actually just solve for the lambdas. Okay, so let's do that. Okay, so this is just a second order constant coefficient ODE, and so we can solve it using the characteristic polynomial. Right, so the solution to this is equal to, you first compute the roots of this characteristic polynomial, and we know that lambda is positive, so we're actually going to get imaginary roots, right? So this leads to plus or minus square root lambda I, but when we have imaginary roots, then you can conclude that your solution is of the form some constant a times cosine of root lambda x plus some constant b times sine of root lambda x. Okay, so this just follows from general theory of ODEs. And now we want to apply the boundary conditions to say something more about the constants and perhaps lambda. Okay, so when we plug in the first condition, f of 0 is equal to 0, right? We get that a cosine of 0 plus b times sine of 0 is equal to 0. But sine of 0 is 0. So this goes away. And cosine of 0 is 1. So then we immediately get that a is equal to 0. Okay. So from here we get that a equals 0. And so we plug in the other boundary condition. So f at capital L is equal to 0, but if you plug in capital L, well, you know a is 0, so there's nothing to plug in here anymore. And over here you have b sine of root lambda L is equal to 0. Okay? And so now if b is 0, then a and b are both 0, then it's a trivial solution, which you want to avoid. So we have to somehow make this term equal to 0. Okay? And so you have to consider when sine is equal to 0. So what we want is when root lambda L is equal to values when sine is 0. So when is sine 0?
Multiples of pi?
Yeah, integer multiples of pi. Okay. So then pi integers. Okay. But then from here we can solve for lambda. Right? So lambda is equal to n pi over L squared. Okay? And since it's squaring it, this doesn't actually matter if it's integers, or you don't want to double count it, so maybe it's better to parameterize it by natural numbers. Okay, and I guess you would have a different lambda for each n. Okay, so this is the eigenvalues, right? And furthermore, we also know what the eigenfunction is for f, right? So we can conclude from all of this that capital F is equal to some constant, but it's going to depend on n, of sine n pi x over L. Okay? I guess n, right? You'd have a different solution for each n. So far, so good?
Isn't that n pi L squared?
Well, we have the roots one over here. So.
Yeah. 0 equals 0?
Well, let's see what happens if you include 0.
Okay.
No. What would happen if you include 0?
0?
Yeah, you get 0, right?
Oh, okay.
So you want to start at 1.
Okay.
Okay, so now that we know what f is, let's move on to what g is. So g is given by this ODE. Where now we know what lambda is, right? You have n many lambdas, so let's solve it for each lambda. Okay. So this you can multiply over and get g prime plus lambda n times I times g equals 0. But this one is pretty easy to solve too, right? In fact, this one is just first order and it's homogeneous, so it's separable. Right? So if we solve for this, you would get something like this. So dg dt is equal to negative I lambda n g. And so if we separate variables again, then we get dg over g is equal to I lambda n dt. So integrating both sides, we get natural log of g is equal to I lambda n times t plus some constant. And so if we exponentiate both sides, we get that g is equal to some constant times e to the I lambda n t. Okay. So what's the difference between the heat equation and the Schrodinger equation, right? Maybe it was kind of obvious what was going to happen because all you do is multiply I, right, in front of whatever your constant would be. So in your solution, right, you get this kind of mysterious looking term, e to the I lambda n t. Right? And so this maybe is a little bit beyond this class, but if you take complex analysis, you'll see that this is what's called unit complex numbers. So there's this formula, I forget what it's called, Euler's formula, where you can rewrite this as some constant, so this part times cosine lambda n t plus I times sine lambda n t. Okay. And so it really is just like if you imagine the complex plane as some subset of R2, then it's some points on the circle. Okay. So anyways, let's combine these two solutions together to get the solution to the Schrodinger equation. So uxt is equal to f times g, which is some constant that depends on n, e to the I lambda n t times sine. So we'll just say this constant just accounts for all the constants, like cn, everything, and bn. So this is sine of root lambda n x. Okay, and the thing about these separated solutions is that since each one is a solution and your PDE is linear, you can add together these solutions, and it's still a solution. So let's just add together all these guys. And that is your solution to the Schrodinger equation. Well, general solution. Okay. So then you would plug in some initial conditions, right? Because we have boundary conditions, but we don't have any initial conditions. So the initial conditions will determine what these constants Cn need to be. Okay. And let's not worry about conversions for this series for now, right? Because the convergence is going to depend on the Cn, right? Like if Cn is 0 for like most of the, so if like Cn is 0 after C2, right? So you only have like 2 terms, right? Then, I guess 1 term. Then of course it's convergent. Or if Cn is like on the order of like 1 over n squared, then it's convergent as well, right? So you have a lot of possibilities here, okay? But the thing to notice is that unlike the heat equation, where this was a negative sign instead of I, right? So if you take the limit as t goes to infinity, for the heat equation this would decay, but for this guy, right, it's not so clear if it's going to decay. I mean, this is already kind of a mysterious thing. Like, what do they even mean to have values in the complex numbers? Right? But at least if you take the modulus, then in respect to t, it's not going away. Right? It's a unit number, so it's always going to be 1. Okay.